Okay, so there are going to be two parts of this video, with the first part being me explaining these two graphs, and the second part being me explaining a graph of the cardiac cycle. So what I first want to talk about is this graph of the SA node with the x-axis being time and the y-axis being the membrane potential of the SA node, or the pacemaker cell. So in the beginning you can see that there's a slow depolarization, and this slow depolarization, otherwise known as pacemaker potential, is caused by sodium ions entering the cell as their slow sodium channels. And as these slow sodium ions enter the cell, this causes a difference in charge between the cell and its environment, which changes the membrane potential. And after a threshold here, after a certain threshold is met, the depolarization of the SA node is caused by voltage-gated calcium channels opening. And these voltage-gated calcium channels cause a large influx of calcium, which causes this depolarization shown. And once the peak of this depolarization occurs, these calcium channels close and potassium channels open. And what happens here is the calcium permeability decreases and the potassium permeability increases. And this causes this repolarization, which occurs here. And then the cycle continues with the slow depolarization caused by slow sodium channels. And so moving on from this graph of the SA node, I'm going to talk about this graph for the ventricular muscle. And so in the beginning you can see that there's this flat line which is known as the resting potential. And this resting potential is caused by potassium channels. And then what happens here with the depolarization is there's sodium channels that open, allowing for a large influx of sodium, causing this depolarization. And then once the peak of this depolarization occurs, there's some voltage-gated calcium channels that open. And this voltage-gated calcium channels allows for a long or prolonged or sort of plateau for this ventricular muscle graph at this particular membrane potential. And the reason that these voltage-gated calcium channels are so important is because with ventricular muscles there needs to be a strong, sustained contraction of the ventricular muscle to allow the blood to be circulated throughout the body. And so that's why these voltage-gated calcium channels are so necessary. And so what happens after this is the repolarization occurs, which is characterized by potassium leaving the cell and these voltage-gated calcium channels closing. And then what happens is resting potential is then again met, and the cycle can continue. And so I'm going to talk about some of the three big differences between these two graphs, with the first being that for depolarization of the SA node, calcium ions are used, and for the depolarization of the ventricular muscle, sodium ions are used. And the next big difference is that with the SA node, resting potential is never met. And this is important because the SA node, or the pacemaker cells, is what determines the rhythm of the heart and the heartbeat. And so since the heart never stops beating, the SA node never has time to reach resting potential. However, the ventricular muscle does reach resting potential, and this is because the ventricles have a little bit more time in between each contraction to allow for a relaxation phase. And then the third and final difference is that the ventricular muscle here uses voltage-gated calcium channels to allow for a plateau at this particular membrane potential. And that's, again, because of the necessity for sustained contractions of the ventricular muscle. So moving on, I'm going to now talk about this graph of the cardiac cycle. And so what I first want to talk about with this graph is this P wave of an electrocardiogram. And what this P wave is it's the depolarization of the SA node. And before this, what happens was there's just the natural filling of the atrium and ventricles in the heart. And then with this P wave comes the atrial contraction. And this atrial contraction causes the pressure of the atrium as well as the ventricle to increase. And the reason that the pressure of the atrium increases is because as the contraction occurs and the atrium is squeezing, this causes the pressure to increase a lot. And the pressure in the ventricle increases because blood is flowing from the atrium into the ventricle, and as this blood flows into the ventricle, the pressure is going to increase. So moving from there, I want to talk about this point on the graph here, where you can see the ventricular volume, the slope of the line modeling ventricular volume over time increases fairly quickly. And this is because as atrial contraction occurs, this is causing the blood to enter the ventricles, and this is going to cause the ventricular volume to increase very quickly. So now I want to talk about this QRS phase of an electrocardiogram, and this QRS phase represents ventricular depolarization, which masks atrial repolarization. And so right after this QRS phase, you can see there's the first part of a heart sound. And a heart sound is composed of two different independent sounds that are known as lub and dub. So the heart sound would be, or a heartbeat would sound like lub dub, lub dub, lub dub, lub dub. And so the lub is known as is characterized by atrioventricular valves closing. And the reason that these atrioventricular valves close is because after the atrium contracts, the blood is then pushed into the ventricle, and since the blood's in the ventricle, the blood wants to go from an area of high pressure, being the ventricle, to an area of low pressure, being the atrium. And because of that, as the blood wants to go up, this causes the valves to get pushed closed. And so you can see here, this is the end diastolic volume, and that's at the end of the natural just filling of the ventricles. And here I want to talk about the increase in pressure of the atrium, and that's because of what I was talking about, the lub part of a heart sound with the atrioventricular valves closing. And so the increase in the pressure of the atrium is because this part of the graph is ventricular contraction. And as the valves are closing, right as ventricular contraction begins, a little bit of the blood is pushed into the atrium, which causes the atrium to increase in pressure just a little bit, which is this hump here. Okay, so moving on, I want to talk about this SV, which is systolic volume, and the systole is the amount of blood, or the systolic volume is the amount of blood as that is moved as the ventricles contract. And next I want to talk about the T wave of an ECG. And what the T wave is the T wave is ventricular repolarization. So this occurs after the ventricles have contracted. And then what happens is the second part of a heart sound, being the dub. And so what happens with a dub is the semilunar valves close. And right after these semilunar valves close, some blood is going to then have a backflow into the aortic valve. And this backflow of blood hitting the aortic valve is going to cause the aortic pressure to increase, as shown here, right after the dichrotic notch. And so the last part of this graph that I want to talk about is the ESV, which is the end systolic volume, and that's the end volume after the systole or the contraction of the ventricles occurs. And so after this point, you can kind of see that the graph starts to just repeat itself with the cardiac cycle. So you can see here, as the ventricles are going to be filled, or the atrium is then going to be filled, and as the atrioventricular valve is open, this is going to cause the blood to flow through gravity into the ventricles. And so now what I want to talk about is how this graph would change during vigorous exercise. So the first part is that the volume here, this is all going to increase. And the reason this is going to increase is because adrenaline is released during exercise. And this adrenaline increases the contractility of the heart as well as the elasticity. And so because of this increase in contractility and elasticity of the heart through adrenaline, this is going to cause the volume to increase as well to allow for a greater cardiac output during exercise. And then another thing that may happen is this pressure is going to increase through exercise. And the reason this pressure is going to increase through exercise is because during exercise the heart is going to need to contract more to allow blood to circulate throughout the body more. And because of this, these stronger contractions, that's going to cause the pressure to increase, because think about like a balloon. If you squeeze the balloon a little bit, the pressure is going to increase a little bit. But if you squeeze it really hard, the pressure is going to increase a lot. And so this is the same thing with the heart during exercise, as the pressure is going to increase. So those two parts are what I think exercise would cause to this graph to change it. So that being the volume would increase as well as the pressure increasing as well.